Welcome to Textbook Engineering Problem, where we explore complex engineering problems and discuss different methods for solving them. In this video, I'll be breaking down a problem and discussing different ways to tackle it. However, keep in mind that there's no one correct path for some of these solutions, and I encourage you to share your own insights and thoughts in the comments. Together we can learn and improve our problem-solving skills. So sit back, grab a notebook, and let's dive into today's problem. Today I'm going to be doing the format slightly differently than I've done in the past. I'm going to try and do like live commentary on what I'm thinking and what I'm doing while I'm looking at the problem. Okay. So the first thing that I'm going to look at is go ahead and read the problem statement. So today we're working out of Elementary Principles of Chemical Processes 3rd edition, and we're doing problem number 5.14. The problem statement says the flow rate required to yield a specific reading on an orifice meter varies inversely as the square root of the fluid density. That is, if a fluid with density rho 1 flowing at a rate, volumetric flow rate 1, yields a root of the fluid density. That is, if a fluid with density rho 1 yields a meter reading phi, then the flow rate of a fluid with density 2 required to yield the same reading is the volumetric flow rate. 2 equals the volumetric flow rate 1 times the ratio of the densities to the squared, or to the 1/2 power. Alright, so the first thing we're going to do here is start writing down our conditions, temperature and pressure that they gave to us in the problem statement. The first stream is nitrogen. We're going to convert that over to SI units. So we start off with temperature at 25 degrees Celsius, convert to SI units equals 298 Kelvin. Then we're going to start working with the pressure here. 758 millimeters of mercury. I'll show you how to do that conversion to turn it into pascals here. And you get certain pressure in pascals. The reason why we're converting over into SI units because they're a little bit easier to use, and I know what R is for I've memorized the gas constant for SI units, so I just go ahead and use everything in SI units and then convert from there after I've got whatever units I want. This second stream here is hydrogen, and we know the temperature and pressure of that stream as well. Convert those over to SI units. Then we've got our volumetric flow rate of stream 1. That's in 350 centimeters cubed per second, so I'm going to change that over into meters cubed per second, so that's also in SI units. We do not know what the volumetric flow rate of stream 2 is, though. So we're going to use that relationship that they gave to us in the problem statement in order to calculate what volumetric flow rate of stream 2 is. However, we don't know what the densities are of these two streams, and that equation relies on density information. So we need to somehow use the ideal gas law in order to figure out what the densities of these streams are. Okay, so density is mass per volume, and the ideal gas law gives us moles. So we're going to have to convert our moles over into masses. And we do that using the molar mass of whatever the substance is. And then we can convert that over into a mass flow rate over the volumetric flow rate. And you can see how we do the algebraic manipulations here in order to get our mass over volume and then start solving for whatever the density is. Okay. So now we've got our equation. Now we can start trying to fill in the blanks. So we start gathering species information. So remember, our first stream was nitrogen, so we're going to gather that in our molar mass of the nitrogen, molar mass of the hydrogen here. Now we calculate what density of stream 1 is, now that we've got all of our conditions and our molar mass. So we just go ahead and write in all of our pressure, molar mass, temperature, gas constant, make sure all the units work out here. You'll see that I wrote down our molar masses in kilograms per mole. That's because gram is not the SI unit, kilogram is the SI unit. So I'm just making sure I'm covering my bases there. Sometimes you'll see me convert it into grams, sometimes you won't. It kind of depends on the application. Because we're solving for densities here, and I'm used to working in densities of kilogram per meter cubed. That's why I converted it over to that. Density of stream 2 is done the exact same way, I just didn't write out the whole conversion there. Okay, so now that we have our two densities, we can use our equation that they gave to us, and we calculate that we've got a certain number of meters cubed per second times the density ratio. That's V1 that I wrote down there, and then we'll calculate, because those densities are in a ratio, their units cancel out, and we get the same units that we started off with was meters cubed per second. So then we need to convert those into centimeters cubed per second, just so that matches what V1 was given in. Okay, so we've calculated what V2 is based on that. Okay, so for part B, now they're telling us, okay, now we're not working with hydrogen gas, now we're working with a gas mixture. And the gas mixture is methane and propane, okay, in a certain mole fraction that they gave to us. Okay, so in order to calculate what our new molar mass is, we need to know what the molar masses of the two components are, and then we need to do a weighted average of those components and their molar masses and how much there is in the stream, according to the equation that I wrote down, the sum of the molar masses times their mole fractions. Okay. And then we do the same thing. That's why you see me here copy paste, just use the new molar mass that we just calculated, and we figure out what density 2 is for this new stream. This stream is obviously going to be more dense because hydrogen is very light and hydrocarbons are quite a bit more dense. Okay, so I go ahead and do the full conversion again so you guys can see that. And then I calculate what the new density is. Okay, and then we've got V2 equals this equation, V1 times the ratio of the density's square root. Okay, and I forgot to write in the scientific notation there, but that's in meters cubed per second, so we convert that over into centimeters cubed per second. And that is the answer to problem number 5.14. Thanks for joining me on this problem, and I'd really love some feedback from you guys if you guys like the new format or not. Thank you for watching. Hope you found this video helpful, and I'll see you in the next one. Thanks.